Traditional database systems rely on pessimistic mechanisms like two-phase locking and timestamp ordering to manage concurrent data access. These models operate on the assumption that if two transactions attempt to access the same data at the same time, they will inevitably interfere with one another. To prevent this, the system forces transactions into queues or triggers immediate rollbacks. Every step requires checking a lock table or verifying a timestamp, creating constant computational drag before any actual work is done. In a workload dominated by lookups, like a student checking course grades, updates happen so infrequently that these locks rarely prevent an actual collision. The system spends more resources managing the locks than it would spend simply fixing the occasional conflict. This inefficiency is why engineers developed the validation-based protocol, which replaces preemptive locking with an optimistic architectural model. Under this protocol, transactions are allowed to execute as if they were the only process in the system, running entirely lock-free. This raises a technical challenge. The system must allow this uncoordinated execution while still ensuring the final database state is identical to a serial, one-at-a-time execution. The protocol addresses this by moving all conflict resolution logic to the final stage of a transaction's lifecycle. To ensure that this deferred resolution doesn't lead to permanent data corruption, the system enforces strict isolation between the transaction's work and the main database. This shifts the strategy from upfront prevention to post-execution validation, altering how the database handles concurrent operations. Safety in a lock-free system depends on this architectural split. Every transaction is partitioned into 3 distinct phases that keep its unvalidated changes separate from the main database. Phase 1 is the read phase. During this phase, the transaction reads values from the main database, but it records any updates or writes only to temporary variables within its local workspace. Because these writes are local, the main database remains unchanged. Other transactions can continue reading the original, stable data without seeing partial or uncommitted updates. Phase 2 is the validation phase. This is the gatekeeper. The system executes a series of mathematical checks to determine if the local updates can be moved to the main database without violating serializability. If the transaction fails this check, it is aborted immediately. The local workspace is cleared, ensuring the conflict never reaches the global data. If validation succeeds, the transaction enters Phase 3, the write phase. Only now are the temporary local variables copied into the main database in an atomic action, making the changes permanent and visible to everyone else. Read-only transactions are highly efficient here. Because they don't have any local updates to copy, they skip this final phase entirely. By isolating writes in this way, the protocol concentrates the risk of conflict within the local workspace rather than the shared database. This physical separation is what makes it safe to run multiple transactions simultaneously without a single lock. To run the validation checks, the system tracks the precise timing of every transaction using 3 specific metadata markers. We track start TS when the execution begins, and validation TS when the read phase finishes and the transaction requests permission to commit. The final marker is finish TS, recorded the moment the write phase is completed. In this protocol, the official serializability order is determined solely by validation TS. By using the time of validation rather than the start time, the system ensures that a transaction that finishes quickly isn't held up by an older transaction that is still slowly reading data. To pass validation, our current transaction, TI, must compare its data access against every previously validated transaction, which we'll call TK. The simplest way to pass is through condition 1, strict sequence. This occurs if TK completes its write phase, meaning it reaches finish TS, before TI even begins its read phase at start TS. Since there is no temporal overlap between these 2 transactions, the serial order is maintained by default. If the transactions do overlap in time, they must meet the more complex condition 2, safe overlap. First, the set of data items written by the older transaction, TK, must have 0 intersection with the data read by our current transaction, TI. Second, TK must complete its write phase before TI begins its own validation phase. This proves that TK's updates couldn't have corrupted what TI was reading, and that TI won't accidentally overwrite the results TK just committed. We can see this in a scenario involving 2 concurrent transactions, T25, which is reading data, and T26, which is performing an update. T26 writes its changes to its local workspace and hits the validation gate while T25 is still actively reading from the database. Because there are no locks, T25 is never blocked. It continues reading the original, stable values from the main database. T26's writes only reach the main database after it passes validation. This ensures T25's view of the data remains consistent throughout its entire read phase. These timestamp checks ensure the system produces the exact same results as a locked database, without ever forcing transactions to wait for lock releases. This architectural approach provides a physical safeguard against a common issue in concurrent systems, cascading rollbacks. Because writes are deferred until the very end, a failed transaction cannot affect the system. Since uncommitted data was never written to the main database, no one else read it. The transaction disappears, and the database continues as if it never existed. However, this optimism creates a specific vulnerability for transactions that take a long time to complete. In a lock-based system, a long transaction can eventually acquire the locks it needs and guarantee its completion. In a validation system, there are no such guarantees. This leads to the problem of starvation. If a transaction is large and slow, short, fast update transactions can repeatedly modify the data it needs. Every time the long transaction reaches the validation gate, it finds that the world has changed, forcing it to restart. To prevent a transaction from restarting indefinitely, the system must occasionally intervene by temporarily blocking those short transactions, allowing the long-running process to clear the validation gate. This is the core trade-off. Pessimistic systems require engineers to manage deadlocks caused by waiting. Optimistic systems require engineers to manage starvation caused by restarts. Strict serializability is possible without the bottleneck of locks, as long as the system maintains clear boundaries between local and global data, and the workload supports the assumption that conflicts are the exception.